it's time. Hello, everybody. Welcome to this session about the energy and local issues. The first speaker is Lucas. Yes?
Yes, hello.
Hello, Lucas. You present the first paper, yes, about regionalized input-output modeling to assess the impact of energy transition investments on the local economy, located Schleswig-Holstein. It's okay?
Yes, it's hard name to pronounce.
Okay, sorry, I'm French. Okay, but you can begin for 20 minutes max, okay? And after 5 minutes for question and answer with the people, okay?
Okay, then I will start sharing my screen. I think now you should see my screen.
Yes, but yeah. Also, we see the presenter on board.
Oh, okay. Sorry about that. Let me just quickly do again.
Put in full screen first, and you share. Yes, it's okay.
Does that work?
Yes, it's okay.
Okay. Just let me drag my brief notes over to my second screen so that you don't see them. Okay, thanks. Okay, welcome very much to the presentation of my paper on regionalized input-output modeling to assess the impacts of energy transition investments on the local economy. And I will be presenting a case study we have done, or to be more precise, we are in the process of doing for the federal state of Schleswig-Holstein in Germany. Us, that is myself and my doctoral supervisor, Professor Reinhard Madlener. I want to take this opportunity to thank everyone, to thank IAEE to give us the opportunity to present here, to thank all of you to attend here, and also thank you, Professor Mayol, for chairing this session. Oops. Huh? Okay. Let's have a look at what I want to talk to you about what I want to talk to you today. I will introduce the motivation behind this study, and in particular, I want to tell you why we chose this region of Schleswig-Holstein as our model region, and why we want to approach our research question with input-output modeling. Secondly, we want to look at the related literature and see which missing piece or which gap this study tries to fill. I will dedicate a slightly larger block to methodology, first to bring everybody up to speed about like input-output models, because it's kind of like a niche macroeconomic application, and then also about regionalization techniques, which we use and which we also want to assess in this study. I will talk about the data that we have used to put into a model, and in the end, I will of course talk about the results, the further work that we are currently doing, and the discussion. Let's first look at why we're doing what we're doing. The paper at hand is part of a larger research initiative called ENSURE. And this research initiative basically tries to explore Germany's electric grid infrastructure until 2050, focusing on several aspects, from technology, so so engineers working there, over society, economy, ecology, and so on. And we have chosen Schleswig-Holstein, it's Germany's northernmost federal state, as the model region in this project. Why? It already has well-developed wind power generation, so all the issues we might be facing with intermittent generation are already there. It has extensive grid infrastructure, and it offers a more or less representative social and demographics structure for the entire country. You might argue, well, Schleswig-Holstein looks very rural, but because it's very close to the urban center of Hamburg, we actually have urban as well as rural regions represented there. If you want to just get a grasp of the region we're looking at, it has between 3 and 3.5 million inhabitants. Yeah, I think around actually in terms of inhabitants and size roughly compares to Connecticut in the United States, if you have a better understanding of what that is. And in terms of the economic structure, like employment rates and so on, GDP per head, it's very representative of Germany as a whole. What we're actually doing is, in this study, is we focus within this research framework on economic aspects, and we do input-output modeling in order to answer the research questions. What effects do investments in energy assets and grid infrastructure have on the regional economy? And because we are answering it with input-output modeling, which is static, we have to put it in the short term, because in the long term, the economic structure can shift, and then the power of this modeling technique to actually answer that question shrinks dramatically. But more on this when we look at the limitations of the study later down the road. Why do we choose input-output modeling? It's a macroeconomic concept. Probably a lot of you have seen it at some point during your education, or probably even worked on it. And it focuses on modeling the interdependence in production and models the network of exchanges between sectors. Now I would like to have a look at the literature related to our study, and in particular, I want to point out two main papers which I want to talk about. I've categorized some references here into 3 broad categories. One is I/O models used in energy and energy economics, then input-output models and regionalization, so different regionalization techniques, and studies on energy and the regional economy. We see that there are a lot of studies on input-output models and energy. One study that has been done at our chair by a colleague of mine and my professor is Madlener and Reinhard 2021, published in Energy Policy, where they did a national input-output analysis of grid investments. They calculated different scenarios for power grid expansion in Germany up until 2050 and looked at the multipliers there. Another study that has also been done at our chair is a regional I/O study on heating systems that was done with regional input-output data, which is available in the survey form for federal state of Austria. And they actually found significant displacement effects, which kind of bring down the overall output multipliers a little bit. And if you look at this overall very broad and in no way complete picture of the related literature, you see that the missing piece that our study tries to address are regional studies for energy infrastructure. We have these national studies using input-output analysis on grid infrastructure. We have some regional studies when survey data is available, but there is like kind of a gap in the literature when it comes to how do we actually perform regional input-output analysis when we don't have survey data and when we have to make do with other techniques to probably find good estimates of the regional impact. This is just a short introduction to I/O modeling in general. I'm probably telling you something that a lot of you have heard before, but some of you might not. So just bringing up to speed, what are I/O models? They are based on input-output tables, and they describe the structure of an economy. what is an input-output table? It's usually obtained from the National Statistical Office or whatever the necessary statistical authority is in the territory you're looking at. Often they are published with a certain time lag. So when we looked at our current study for Germany, the most up-to-date data, which is fully available, is of 2017. We hope that the 2018 data is coming out relatively soon, but it takes a lot of time for authorities to process information, pass it on, and until it is compiled into this big input-output table describing the entire national economy, it takes some time. What it actually does, it shows the production by sector and how products of every sector are used in other sectors or used for final consumption or used for imports and exports. Brief overview of what input-output modeling tries to do. The central assumption in input-output modeling is that we have constant technology in the short run, at least, or that is the assumption. It is most believable in the short run, and that's what you see here by our equation describing our Aij, that the share of what sector I produces and gives to sector J as an input to the production of sector J, and the overall production of sector J is constant. If we then take the very simple arithmetic relationship, transform it a little bit, and I've written out the actual big matrix form here once because for a lot of people it's easier to understand when they see the big matrix, is that we obtain a system of linear equations which actually describes the production transactions in the entire national economy. So we have our big equation X is a function of A, like the matrix which describes our technology, if you want to say so, in the national economy, of X, the intermediate inputs, plus F, which is the final demand. So how do we actually make it into a model to actually find something useful about it? We want to usually look at production by sector as a function of demand with some very easy mathematical operations. We can transform the equation we had just now into the following form, that X is equal to L times F, and L is the so-called Leontief inverse matrix in honor of Vasily Leontief. And this matrix describes the output multipliers of a demand shock given to this economy. So for the national economy, it's relatively easy, but the challenge we're facing when we look at regionalization is estimating L or A and then getting to L for a single region without survey data. And the central assumption that a lot of these regionalization techniques make is that there is some kind of linear relationship with the national technical coefficients. And this linear relationship is described by this factor T. When we now look at different regionalization methods, one of them is the simple location coefficient method. And what we try to do is describe this factor T in order to calculate the regional technical coefficient matrix as a function from the national coefficient matrix, which is there. Basically, sorry. So what we basically assumption here is that the less supply of a certain good originates from one's home region, the weaker this sector is represented in one's own region. And in an extreme example, assume that you have a region without any production of a certain good, then all of the inputs have to come from other regions or from abroad. And the comparative value which we put into our model here is then the share of this sector's production in the region as part of the share of this sector in the entire national economy as part of the entire national production. This is what you see in this equation here, described as SLQ, and this stands for the simple location coefficient. There are certain limitations to these techniques. They don't account for cross-hauling. Cross-hauling happens when you have the same sector importing and exporting at the same time, so that if you look at the overall net export data you might have, it might give a very skewed image of the actual transactions going on. Then there is one method to try to ameliorate this problem, has been invented by FLAG, therefore called the FLAG location coefficient. And they basically assume that the smaller or bigger the relative size of the sector and the relative size of the receiving sector, therefore the bigger or the smaller is the likelihood of supplying the goods in question. And the second assumption is that regional supply cannot exceed national supply. What they came up with is given here on these slides, and you might wonder why you have at some point just like why it varies for IJ. Oh, there's actually a slight mistake on the slides. I will correct that for the final version. Why you have two different formulas. The second formula is for the entries on the diagonal of the matrix, because there you would basically divide SLQI by SLQI and just have one, and therefore lose a lot of the information you might actually gain from actually looking at the regional data. Again, the problem here is that you have relatively strong assumptions on cross-hauling. So the model basically gives you very, very strong assumptions on how to model cross-hauling, and it's not clear whether these assumptions are actually represented in reality. A third method I want to briefly touch upon is the so-called CHARM method, or cross-hauling adjusted method. It's the most recently developed method to regionalize IO data, and it basically tries to use other available regional data, most commonly used regional employment data, as a percentage of national employment data to scale down entries in the overall in the national input-output table to actually receive a regional input-output table. Important here is that you look at the balance of imports and exports to actually measure intra-sector heterogeneity, and this measure of heterogeneity can then help you to estimate the extent to which you have cross-hauling in your local region. The idea here being is the more heterogeneous a sector is, the more heterogeneous a sector is, the cross-hauling effect increases, since some goods in that sector tend to be export goods, others tend to be import goods, and they cannot be substituted for each other when the heterogeneity is high. Due to timing constraints, I would like to come to actually results now, so that I don't get far too much over my time, and look into the data we used for our study. The macroeconomic survey data we got has been taken from official sources, from the German National Authority and the regional authority for that region. National IO table, again, was available in a very, very high resolution. And the problem was that the regional economic data published by the regional statistical authority was only available in a much lower resolution, sometimes incomplete, especially with respect to trade and employment data, and had inconsistent classifications sometimes. So what we had to do, we had to harmonize and reclassify some things to bring these two survey data sources together. What we actually wanted to do is we wanted to look at, if we actually build a project in that region, what are our multiplier effects? So we needed the project-specific investment data, and that is not very easy to come by, but we collected investment data from various reports and projects. Some of them were actually, thankfully, available on a very disaggregated level. Often in terms of components, how much certain components to the two examples we have is solid state transformer. We want to do a solid state transformer is a power line and a wind park. They are available on a component basis, and then we classified them according to the production sector. If there are future expenditures, we discount them with the calculatory interest rate according to the National Grid Development Plan, which is given there. And in order to make the results comparable, because we don't want to say this project induces that much, but we want to look at the representative euro. We normalize the costs and can basically calculate the project share of costs, the sector share of costs per project, and put that into the F vector, and our F vector sums to 1. Therefore, the multipliers we look at basically show the average euro spent on this construction project gives us this amount of actually output multiplier.
Excuse me, Lucas. Lucas, just to keep the time, if you just conclude or give the main results very briefly to let the time to question and
yes,
to keep the time. Sorry.
Yes, no problem. 2 minutes, I'll be ready. Yes. Okay, so what we actually did is we are currently in our first step. We calculated the total output multiplier effects for different values of this parameter delta in the FLEC formula and compared them with national results. And you see that they are all much below what we are, they are much below the national sector, which is actually what we are expecting. And for the reasonable values for this delta multiplier for a region of that size, we see that about 25 to 30% of the induced effects actually stay local. Interestingly, also that energy assets have an above average multiplier effect. On this chart, we actually graphed the dependence or the role of the delta in the location quotient formula. Also looked at methods, especially simple location quotient, which are known to overestimate it, to actually see whether our method is consistent and whether our estimates make sense. And here you also see that we can exclude delta smaller than 0.5 and that our estimates are overall in the same ballpark. Further work in process, if you are interested in that, please refer to the paper which our chair has done before. We basically want to take this and use these regionalization estimates to do what we've done in this paper on a regional level. That means we want to look at employment multipliers, the operation phase, fiscal multipliers, and expand that to a partially closed IOM, which means you have a partially included household sector and so on. Displacement effects we consider not that important for local research because if you consider a public expenditure, the costs need to be recouped nationally. So the costs which actually fall on the local population are quite low. For the discussions, we would like to have empirical survey data to corroborate our regional estimates. The main problem we see is that we don't include the changing structure of the economy. So it's really just like a short-term look at what's happening. Policy implications, we think that the effects on the local economy are small but noticeable. And further research and actually communicating that could ameliorate regional transition to these infrastructure projects. And further avenues of research means, we want to corroborate the method with in regions where there is available survey data. You want to expand it to dynamic IO modeling and probably perform structural change analysis. And ideally, we look to find a way to actually estimate the optimal, that is error minimizing parameter delta. And I think this concludes.
Thank you.
Thank you very much.
Thank you for your presentation. Do you have any question for Lucas? You can write in the chat, or Adam? No?
Thank you very much. I'm trying to share my screen.
Oh, I should probably stop sharing.
Yeah, you need to stop sharing, right?
So sorry about that.
All right, so give me another second. Let me try one more time. Okay, I'm good. I'm good.
Adam?
I'm good. Can you hear me?
Yes. Just
yes.
Adam,
yes,
1 minute.
Perfectly.
1 minute. Any questions for Lucas, or it's okay? Okay. Well, thank you, Lucas, for your presentation. And we continue with Adam.
Thank you very much.
I'll let you.
Hi, everybody. Can you hear me?
Yes, it's okay.
You can hear me. Can you hear me?
I can hear you.
Yes.
Yes, very well.
All right. All right. I also want to make sure my co-author Dan Way is on the line, but I guess she'll be here in a moment, hopefully. So good morning or afternoon, depending on where in the world you live. I'm happy to be here today to present, along with my colleague Dan Way, the Los Angeles 100% renewable energy study, economic impacts and jobs. So this study was co-authored with a couple of other people mentioned here, Harvey, Cutler, and Martin Shields at Colorado State University, and David Kaiser of the National Renewable Energy Lab. Now I'm having trouble moving my slides. Oh boy. I'm sorry. I need to put this in slideshow. Okay. So by way of background, this is or an overview. I'll be covering these various sections, focusing on the 9 modernization scenarios, the models used, and there are 2 of them: a computable general equilibrium model and a specialized job impacts model. I'll be talking about the input data, the aggregate economic impacts, the disaggregated impacts across socioeconomic groups, workforce impacts, and then conclude. By way of background, the city of Los Angeles intends to modernize its electricity infrastructure by going to an all renewable platform by the year 2045. It's also implementing aggressive electricity targets for buildings and vehicles. That's the demand side. I'm going to focus on the supply side in terms of all renewable energy. So this is consistent with California Senate Bill 100. That's where the study gets its name, which is basically calling for zero carbon resource base for retail electricity sales by 2045. And Los Angeles is the leader in the state thus far in terms of actually specifying and working out a plan to implement. As I mentioned, I'll be considering 9 alternative modernization scenarios under consideration. And just wanted to mention that this study has many areas of analysis underpinning it that I'm not going to be able to talk about today: an extensive engineering analysis, the economic impact that I will be providing, but also an environmental impact analysis including the demands for water and the impacts on various stakeholders. So this is kind of a busy slide, but it lists the 9 scenarios across the top. And what we have here is that you'll see that there are several types of electricity generation that are common to all of the cases, and these are typically the renewables. On the other hand, some scenarios where we say it's 100% electricity, some scenarios allow for gas-fired peaker plants, for example, and some allow for biofuel combustion, and some allow for maintaining the existing nuclear facilities. So these are, in fact, the nuclear are essentially zero carbon. The question of whether they're renewable or otherwise clean is debatable. But you can also see that the most likely, the scenario that's most like the status quo is this SB 100 scenario to keep in mind, because it calls for the retention of all of these variable technologies that aren't in some of the other cases. We're using 2 types of models, the computable general equilibrium model and the JEDI model. Both share common sets of underlying data, and both are needed. We need the CG model to give us the overall economic impacts, and the JEDI model to give us employment specific impacts. So the CG model is fed into that model, and I'll describe the model in a minute, are potentially positive impacts from investment, operation, and maintenance, and price decreases associated with some of the scenarios, and negative impacts from cases where there are price increases, and also electricity displacement. So for those scenarios which call for shutting down the gas peaker plants, we have to factor in that people will be unemployed directly and indirectly as a result of that. And as it notes, the CG model is economy-wide. So the JEDI model, on the other hand, is used to estimate workforce changes both in and out of basin. That's the Los Angeles basin, the Los Angeles metro area, even though we focus on the county. And the gross impacts only account for positive outcomes such as jobs created and supported by the scenarios, because it's mainly an assessment of workforce needs and training. So the negative impacts on jobs are factored into the CGE analysis separately. Both models are parameterized with the capital and operating maintenance costs from rooftop solar and capacity planning models for all of the other renewable sources. And essentially the CG model incorporates cost data that associated with the scenarios, some positives and some negative with respect to electricity prices. CG modeling is considered the state of the art of economy-wide modeling. It captures all the best features of IO, such as the multi-sector detail, the accounting for all inputs and the interdependency, but overcomes the limitations of linearity, lack of behavioral content, for example. And so this is a circular flow of the economy diagram you often see, but the thing is a CG model can incorporate all of those features. Some specifics of the CG model: there are producing sectors on the order of about 80 of them in the model, and they generate output using labor capital intermediate inputs. And we use a CES, a constant elasticity substitution production function. Households earn income and then turn around and consume various kinds of goods. Electricity expenditures, just by way of looking at elasticities and shares of electricity in the household budget, typically increase with household income, but they're a larger proportion of low-income households, and that has expenditures, and that has a great effect on the income distribution impacts. One of the key things we needed to do early on is to choose a reference scenario or reference base for our impacts. And we realized that if we used just froze prices as they are now, that wouldn't be very realistic, and it would give us biased results, which would show increases in electricity prices in all scenarios. So even in the absence of this initiative, there would have been progress on incorporating renewables into the energy mix. And so hence what we did was we chose SB 100 as the minimal compliance or reference scenario. But we did also calculate the impacts in relation to 2020 constant prices as a sensitivity test. So these are the basic results of our analysis. And I just need to move something so I can put my cursor on here. And as you can see, some of the these are basically the price changes. And let me catch up with some of the features of the Zoom are obscuring some of the text for me, but these are basically the price changes of our various scenarios. And you can see that some call for positive increases as high as 25%, and some call for negative impacts as high as, and again, I say 25%, as high as minus 15.6% for the case of the SB 100 stress. So Dan, I hope you're on the line and you can take over the rest of the presentation. Just a second, I want to make sure that my co-author is here. By the way, how much time do we have? And Dan, are you on the line? Can people still hear me?
Yes.
Yes, we can hear you.
Oh, we can hear you.
And the time of presentation is 20 minutes plus 5 to 10 minutes to questions and answers.
Yeah, you have a 10 minutes max. Your microphone, please, if you want to speak.
Adam, your microphone is muted. I don't know if you're
Muted now.
speaking.
All right.
Yeah. Okay.
All right.
Great.
So thank you. So these are the basic impacts, and in terms of average annual employment gains and losses from the various scenarios. And you can see in terms of average annual employment gains, the SB 100 stress scenario will yield during the final compliance period on the order of 6,000 jobs. On the other hand, the largest negative one is a case where you have kind of forcing the issue with some early compliance, but not allowing biofuels and some of the other technologies that are lower cost to enter. In that case, you get a reduction in impacts in terms of jobs. So I might say the other thing to look at is the far right column, where you see that none of the impacts in terms of percentage changes are more than 0.5%, positive or negative. By the way, this is the 10th study we've done of the job impacts of what we call climate action plans, which include things like RPS and cap and trade in the literature. These have been published over the years in climate policy, the economics of energy and environmental policy, energy policy. And we've typically found results like this. So there's a large debate that often gets polarized, where many people say, well, green jobs are a panacea. So if you implement something like this, you'll create tens of thousands, if not hundreds of thousands of annual job years. And on the other hand, if you there's a group that says, no, these climate action plans are very detrimental to the economy. They're job killers and are going to lead to massive unemployment. And it turns out that in those 10 studies, which are done for the Florida Governor's Office, the Michigan Department of Environmental Quality, when Granholm was the governor, she's now Secretary of Energy, Pennsylvania, Southern California Association of Governments, New York State. In every one of the studies, we found that the impacts were going to be less than 0.5%. So neither of those polar extreme arguments hold. What you have is typically these results that are either positive or negative and fairly minor. And actually, in most of the studies, more than 80% of the studies, the job impacts were positive, but less than 0.5%. So in terms of the income distribution analysis, and I just need to move something again. What we find is that for the SB 100 high example, this is a good example, the percent change in terms of the income when you have some negative price increases favor low-income households and actually help the income distribution. On the other hand, when you have high price changes, or when you have positive price changes, you have a disproportionate effect on the lower income groups. And that's not surprising, again, because lower income households have a higher proportion of their income devoted to energy because it's a necessity. So we also look at Gini coefficients because sometimes it's hard to see exactly how the income bracket effects shake out. And so we use the Gini coefficient as a one parameter depiction of income inequality. The baseline Gini coefficient for LA is 0.4582, which is approximately the US average. And so the changes in Gini coefficients in terms of inequality are very small, ranging between 0.05% and 0.25 of 1%. So they're small as well, but they can go either way. This is a little more on the income distribution impacts, and it just cements what I've just said. And so let me go to the conclusion, and that is that the compared to the SB 100 reference case, we project very moderate, or even I might say modest, employment impacts of the LA 100 scenarios. And these are going to vary from nearly 3,600 average annual job year losses in the early and no biofuels moderate scenario to 4,700 annual job gains in the SB 100 stress scenario, be over the entire planning horizon 2026, 2045. Those numbers are a little different than what I mentioned before because I just called out the highest 5-year periods. But if you average it over the entire 20-year period, these are the bounds of job gains and losses. The time paths of changes in economic impacts are affected by 3 main factors: the capital costs, operating and maintenance costs, and the cost increases translated into price changes. And I should have said cost changes translated into price changes, both positive and negative. And it turns out that the changes in capital investment are the factor that's most influential. So although many of the aggregate impacts are large in absolute terms, 6,000 jobs is nothing to sneeze at, they are relatively small compared to the overall very large Los Angeles economy. And basically almost all of the impacts over all the time periods for all the scenarios are less than 0.5% compared to our reference base. So with that, I've concluded, and I'm happy to answer any questions.
Thank you very much, Adam. We take questions in the chat or. No, any questions? Okay. Well, thank you. Wait, okay. Yes, a question in the chat.
Oh, okay. Let me go to the chat. Okay, I need this. Oh, boy, stop sharing my screen. Anyway, in the chat. Oh, how do you
Madlener, I can unmute myself and ask the question directly if you like.
Oh, no, that's how I can. How do you account for the trade flows in and out of the city of LA? So that is done with, I'm gonna have to remind myself in the CGE model in this case. So I don't know if you've heard of IMPLAN in the United States. It stands for Impact Analysis for Planning. It's been around for 40 years, and it is the largest commercial source of input-output data. And it includes data on interregional trade flows. So on imports and exports in and out of the region based on the regional purchase coefficient approach, which is considered one of the more solid approaches to regionalizing input-output tables. So if you read any CGE modeling or practically any IO modeling in the US will use IMPLAN.
Is it county level or a level higher?
What level? Oh, well, yeah. What we did is the county and the rest of the US and the rest of the world.
Okay.
Okay.
Yeah,
thanks for the question.
Okay. Thank you very much, Adam and the others for the question. I propose to continue. It's Anne.
Yeah. Yes. Hi to all. It's my turn. So first of all, I unfortunately have to switch off the camera because during the whole day I'm experiencing massive connection issues. So I think it's better if I switch it off. Yeah, so I'm Anne Nieters from the Fraunhofer Institute for Manufacturing Technology and Advanced Materials. It's called IFM, and I will share my screen. Okay. So do you see my presentation? Hello?
Yes, yes. But
yes.
It is not in full screen. If you can.
Yes. Better?
Yes, it's perfect. Perfect.
Okay, fine.
It's okay for 20 minutes.
Yeah. So first of all, welcome to my presentation on effects on local value added and employment from transforming energy supply in an urban neighborhood. yeah, first of all, I will give you a short overview. I will, at the beginning, I will give you a brief insight into the project Croé 100. In its context, the effects are determined, and then I will tell you, or will give you some insight in the method we used. It's an additive method. It's not that popular than the other methods we've heard about, and it's derived from the GDP expenditure and distribution approach. Following this, I present selected results, and finally I summarize the results and come to a conclusion. So the project Croé 100 or Croé 100 is a 5-year research project funded by the Federal Ministry of Education and Research in Germany. And the research focus is the transformation of the electricity and heat supply system, as well as the mobility of an existing neighborhood in the city of Heide. The existing neighborhood is called Rüsdorfer Kamp, and the city of Heide is in the federal state Schleswig-Holstein. We've already heard about it. And the core of our system, or the core of the transformation system, is a local heating and electrical operating grid. We have PV on the roofs, and the PV systems supply electricity directly to a large heat pump. The generated heat is temporarily stored in a large-scale heat storage unit. And in case thermal storage is overloaded, we have as well a battery storage, which buffers the PV electricity. Of course, we consider as well the sector coupling, and this is achieved by means of electrolysis. And in case if no PV electricity is available, the large heat pump is supplied by means of a CHP system. And last but not least, you can find a gas boiler, which is used for redundancy or a temperature increase on cold days. To analyze the effects, the regional effects, we have so far focused on the construction and operation of a new heating grid. And we compare 2 scenarios. One is the business as usual scenario, which is characterized by a conventional heat supply, and the renewable scenario, which also uses alternative technologies. So in the table, you can find an overview on the components. In the renewable scenario, we have the boiler plant, the CHP, electrolysis, the heat pump, the operating grid, of course, and the PV. And in the business as usual scenario, we have only the boiler plant and the CHP. Okay, now to the method. We estimate the regional value added, as I've already mentioned before, and there are, of course, numerous definitions of value added, and we focus on the definition derived from national accounts. So the values that remain in the region and do not flow out of the regional economic cycles. And the advantage is that compared to investment and corporate indicators, it enables more precise statements to be made about the effects of entrepreneurial activities and success and on the regional economy. And of course, the value added flows off if, for example, the individual steps of installation and operation activities are taken over by external actors, meaning by companies which are not located in the city of Heide, for example. And the concept of regional value added supports municipalities in achieving the climate protection and the self-sufficiency, and of course, strengthening the regional economy. Now you can have a look on the method for calculating the value added. as I mentioned before, is not that popular, but we think it's suitable in the context of a neighborhood, which we are studying in this project. And according to this method, the net value added is made up of the production factors, capital and labor, as well as the share of the state in the form of taxes and other levies and income, and so on. And the entire model considers the operating phase of the respective renewable energy plants, which I have mentioned before, as well as the investments in these plants. And the revenues which are relevant for the calculation of the value added are derived from the different items of the operating and investment costs of the respective renewable energy technologies. So it's like insurances and law and tax services, administration, and so on. And yeah, the identified effects are differentiated into direct, indirect, and induced effects, as you can see on this sheet. Yeah, we have the direct effects that are the profits, which is of course the difference between the income from the sale of heat and the costs. We have the interests, which are paid on borrowed capital. We have the income, firstly of the operating staff and as well of the construction staff. And we have, last but not least, the business taxes, which have to be paid by the companies, or the income taxes, which have to be paid by the staff or by the employees. Yeah, on the other hand, we have the indirect costs, and we estimated them on the basis of the regional shares of material costs and incomes. So the cost rate, for example, for the maintenance activities of a renewable energy plant is split into personal and material cost components. On the one hand, this separates the employee income and the associated social security contributions. And on the other hand, the material costs are determined as sales revenues of the supplier companies in order to determine the further indirect value added effects. And the breakdown into personal and material costs is technology specific for each cost item of the operating costs. So we have a lot of costs which we consider. And the personal and the material cost components were regionalized. So we made an assumption concerning the level of regionalization. And then we have the third component, that are the induced effects. These effects arise from the expenditure of the income included in the direct and indirect effects in the region under consideration. So the city of Heide. And the induced effects are determined on the basis of a multiplier approach from macroeconomic theory, which results from system of equations for the equilibrium analysis of aggregate demand and supply. So we have the multiplier, which consists of from regional import quota, indirect tax rates, marginal consumptions, and so on. Yeah, that is the method. The method for calculating employment effects seems to be a little bit easier. We estimate as well direct and indirect employment effects. So we try to answer the question, how many full-time positions for installation and operation of equipment and components are necessary. And the basis are employment intensities of the relevant sectors, which are derived from public statistics, and we converted them into full-time equivalents. Yeah, you can find a rough overview on some employment intensities. So that means employees per million euros turnover. And the turnover is, in our concept, the costs minus the profit margin. And we already made assumptions according the profit margin of the companies. Yeah, that's the method. Okay, now I can find, or now you can see some of the results. These are results of the regional value added in absolute terms for the year 2022, and you can see that the renewable scenario generates more value added than the business as usual scenario. 8.1 million euros versus 2.5 million euros. This is, how I said before, the year 2022, so the year in which all plants are installed, and it's the very beginning of the transformation, and then you can find the value added during operation, and that are effects which are generated by the service and maintenance activities, legal and tax advice, and so on. And the value added is roughly from 450 to 500,000 euros in the renewable scenario. In the power scenario, it is at the beginning a bit lower, 220,000 euros, and you can see almost a doubling until 2035. And the main driver for this development are the increasing fuel costs. The employment effects, as you certainly can already imagine, the direct and the indirect employment effects in the renewable scenario are much higher. So we have 96 persons, or we need 96 persons to transform this heating grid or this heating system directly in the period from 2022 to 2035. In the business as usual scenario, that are only 25 people. The indirect employment is a little is less, with 30 people versus 11 people in the business as usual scenario. And the question is, how looks the composition of regional value added like? And you can see that the main driver of the direct value added are the personal expenses, so the income for the people who are engaged with the works, with the installation or the operation. And the business as usual scenario, we have as well the profits, which are striking. And concerning the indirect value added effects, we can see that the income is quite relevant to the value added, especially in the renewable scenario. And that is the composition. And then we try to find out which components the drivers of the value added and the employment are. And as you can see in the renewable scenario, it is the heat pump with 7.8 million euros, followed by CHP and electrolysis. And in the power scenario, it's the boiler plant, indeed, with 5.1 million euros. In principle, you can generate higher value added and employment through cost-intensive activities. Therefore, we consider the whole thing per euro invested. So, that's the next slide. So here you can see the value added in the city of Heide in relation to the costs, to the investment costs and the operating costs. So the question is, which components contribute the most per euro invested? And yeah, you can see that the highest amount can as well be recorded in the case of the heat pump in the renewable scenario, and with 0.633 euro value added per euro invested. And you can see that the boiler plant in the business as usual scenario has higher values than the other components in the renewable scenario. Yeah, so the question is, what about the employment? Yeah, which components offer the greatest employment potential? That is, of course, again, the heat pump due to the high investment costs, 62 versus 18 and 19 and 2, the renewable scenario. And yeah, the boiler plant is the main driver in the Bauer scenario. Then we have undertaken several sensitivity analysis, and yeah, here you can find the results of one example. We we had initially costs for insurance, administration, legal and tax advice, and miscellaneous. We called them non-specific operating costs from 0.5 to 1% of investment costs, and we increased them to, or we set them up to 1.5%. And the main effects can be or happen during the operation phase. So from 2023 to 2035, you can see that the renewables generate approximately 750,000 euros annually. And yeah, the Bauer scenario starts a little higher with 300,000 euros in contrast to the former calculation, to 400,000 euros annually, and you can see definitely a lighter increase than before. And the thing is that the profit, or the regional profit, is decisive for the effect of the variations. Yeah, I already come to this summary. So yeah, we found out that transforming the heating system from a conventional to a durable one holds potential for value added and employment. In the Bauer scenario, 6.8 million euros, and the renewables 40 million euros, approximately 100 full-time equivalents, and the Bauer scenario 26 full-time equivalents. The main drivers are the installation and operation of the heat pump, that the heat pump generates more than 60% of the value added, because it is the cost-intensive component, the most cost-intensive component. And in relation to the costs incurred, the potentials are greatest for the heat pump in the renewable scenario and the boiler plant. And as I've shown in the slide before, the profit in the scenarios is decisive for the effect of the variations. For example, the increase in non-specific operating costs only affects the regional value added if the profit is more than zero. And yeah, indeed, higher operating costs can lead to higher value added. So that was my presentation. Thank you. And any questions?
Thank you, Anne. Do you have any questions for Anne? You have a question in the chat. I don't know if you... Did you see the question of from Reinhard?
No.
In the chat?
I can unmute.
No.
And the question is, can you say anything about where the jobs are created? Where?
In different sectors. So can go
No,
back
I mean
to
locally, regionally. Can you
Yeah.
say anything whether they're abroad, domestically in the
No,
region?
that are really regional data. So really the regional employment. So so yeah, there are some assumptions concerning the regionalization level of certain activities, and yeah, we have some information about the employment in Heide and from companies and so on. And I think that our assumptions are quite realistic, which were implemented in the calculation. And that is really the regional employment in Heide and in the I don't know the word in English, the Landkreis, Dithmarschen Landkreis. Is it county? I don't know.
Yeah, I would say county, but
Yeah.
you would need to know where the heat pump or the wind turbine is manufactured and whether the
Yeah, that is no.
company
We don't.
has an affiliation there, or
No, we don't. We don't consider the manufacturing of the components. We only concentrate on the installation of the plants and the operation phase. So if we buy some plant or components from the Bavaria, for example, that has no influence because we only focus on the installation.
Yeah, and you don't know much about the transportation value added, right?
No.
So maybe you're safest on the operation and maintenance effects, but less so on the investment ones, right?
The investment, yeah, but the investment in
Because
installation, so not in the production
well, the investment,
of components.
if you don't know where the investment, the capital comes from, where the products come from.
Yeah, that is right.
Then you can't say much about it, but you might be safer on where the workers came from, and maybe also concrete, etc., is easier to estimate because they will not come from very long distances.
Yeah, that is
low value, high volume components are more likely to be produced and supplied locally, I would assume.
Yeah. Okay, so I can't see the chat. Yeah, any questions? More questions?
Yes. No questions? Okay, thank you, Han, for your presentation and discussion.
Okay,
we can
so
finish by the... Yes, sorry.
I have to quit my the sharing, right?
Yeah.
Of my screen.
It's okay. Yes, we can.
Okay.
Right. Thank you.
I did it already. Thank you.
Ah, fine.
Okay.
Okay, great.
Thank you. And now we have the last presentation, last but not least, Zixuan, also for your last presentation, you can share your screen.
Yeah. I'm trying to share my screen.
The white wolf.
Here, can you see my presentation?
Yes.
Okay, perfect.
It's okay. You can begin for 20 minutes.
Okay, thank you, Alexandre. Hello, everyone. Good afternoon or good evening, depending on your time zone. Firstly, I would like to show my gratitude for the IAEE conference for organizing this wonderful online event. So today, I would like to present to you one study in the framework of my PhD thesis concerning optimal decarbonization of French residential heating sector till 2050. And this study is co-authored by my PhD supervisor professor, Dr. Eddie Asmou, at Center for Applied Mathematics, PSL Research University in France. And the title of my study is Accounting for Social Technical Nodes in the Future Sustainable Heat Strategies for French Residential Buildings. So next, I would like to shortly introduce the plan for this my conference presentation. Firstly, I will introduce the general context of our study, including some key information of the French residential heating sector, its political and environmental background. And next, I will illustrate some different aspects of French traditional heating sector, including some technology and social economics data. And secondly, I will introduce our modeling method and research goals for our study. And at the end, I will demonstrate some of our preliminary modeling results and give conclusions. So I would like to firstly present to you the French national final energy consumption and carbon emission balance. So as you can see from the figure, residential sector is a very large energy consumer and a considerable carbon emitter in France, as well as the transport sector. So in 2018, the residential sector accounts for about 28% of national final energy consumption, and it also accounts for about 13% of national carbon emission. As well as for the transport sector, it's the largest carbon emitter in France, and in 2018, it speaks for more than 80% of national carbon emission. And the final energy demand of French residential sector consists of 4 parts, including space heating, domestic hot water production, cooking, and specific usage of electricity. So the figure on the left represents its final energy demand level in recent years. As you can see, space heating accounts for the majority part of residential final energy demand, and its consumption level is very closely linked with climate conditions. And the consumption level of the other usage is quite stable throughout this period. And the residential heating sector is still a very carbon-intensive sector, as illustrated by the figure on the right hand, which is the distribution of heating equipment in French housing stock. So as you can see, more than 40% of French households still use natural gas as their main energy resources, and some very carbon-intensive fossil energies, such as fuel oil, liquefied petroleum gas, and coal still accounts for a very considerable market share in France. So in parallel, after its participation to Paris Agreement, the French government introduced very ambitious goals on reducing national carbon emission. So the SNBC, which is the national roadmap of decarbonizing all energy sectors, set some objectives to achieve zero net emission by 2050. And for the residential tertiary sector, some similar requirements have been put forward. So this sector will be totally decarbonized by 2050. So what will French residential heating sector be like in 2050 under this strict environmental constraints? So according to SNBC, which also gave details on how residential sector will reach the complete decarbonization by 2050. Firstly, there will be a significant improvement of the thermal performance of French housing stock as a result of energy retrofits. And secondly, there will be a massive introduction of high performance heating equipment, such as condensing gas boiler, micro CHP, and so on, and renewable energy sources such as geothermal, wind, and solar energy will take the majority market share. However, all political planification and prospective studies existing now, the SNBC scenario only represents one possibility, and in our study, we will try to explore more possible solutions under this given technological, economical, and environmentally constraints. And given the status quo of French residential heating sector, our prospective modeling study tries to study low carbon strategy with an improved model of technological choice and investment decisions for French household by firstly disaggregate French housing stock by our predefined key social economic criterion in a bottom-up energy system model, which is Times France model. And I will try to illustrate the model afterwards to you. And by our modeling result, we try to evaluate the technological transition pathways to achieve some very ambitious decarbonization goals. And in our study, all the carbon emission in our scenarios will be close to zero net emission till 2050. And we use TIMES model as our main modeling tools. So TIMES model is a bottom-up model which could characterize the complexity of one energy system, and it can achieve a technical economic optimization with under demand-supply equilibrium over a defined time horizon. And the temporal, geographical, and sectoral definition of time model is very flexible. And the model also allows the commodity flows among regions. So it's very convenient for us to model energy system with TIMES model. And the time model's optimization process is under the condition of minimization of the total discounted cost of the energy system, as illustrated by the linear objective function in the middle. So here is a simplified schema of TIMES France model used by our study, and it is a model developed by Center for Applied Mathematics and could present the whole energy system of France. So it's bottom-up model, and in which the primary energy sources used in the energy system could be either imported or produced locally and then transformed by a different technological process into the final energy used by different economic sectors. And in our study, we try to give some new information or update the residential and the transport sector of the TIMES France model. And the cost minimization process of TIMES model is under certain or specific political, economic, and technical constraints. So we have identified that the household income level is closely linked with the residential heating strategy and individual mobility strategy. And the household income level is a very decisive factor on residential housing choice, thus influencing the heating equipment and thermal performance of the dwelling. And the statistic results of some existing national housing survey indicates that the income level is closely linked with the thermal performance level of the housing, as illustrated by the figure on the right. So basically, if we separate the French households into two groups by decile of per consumption unit income, so group 1 contains the first and the second income decile household, and group 2 for the rest of the household. And the energy performance level of group 2 housing is generally better than that of group 1. So as shown by the figure. So for our model, we use the same strategy to firstly, or to give some first disaggregation of the French household into this two predefined group. So the group 1 is rather some less of families of D1 and D2, and the group 2 is from D3 to D10. And the energy consumption and socioeconomic data used in our model is calibrated from existing results of some national scale housing survey and transport survey. So in our first study, we'll try to explore 4 scenarios with regard to discount rates and carbon emission constraints. For the discount rates and for the first 2 scenarios, which is scenario A and B, we will take the social discount rate, which is fixed at 4.5%. And for the rest 2 scenario, we use the implicit discount rate as interpretation of household access to capital. So the implicit discount rate is type of discount rate widely used for residential investment in energy efficiency, and it is a reflection of all influential factors on the residential energy efficiency investment decisions, including income. So in our study for the first house group, we use 20% as a discount rate and 10% for the second house group, which means that the household in group 1 will have less access to capital in investing in energy efficiency. And for the carbon constraint, firstly we use two scenarios. The first one is a high carbon tax, in which the carbon tax of 2050 will reach to 200 euro per ton. And the second one is a carbon neutrality scenario. Next, I would like to show you some of our preliminary modeling results. So the first results that I would like to present you is a final energy consumption level for all energy sectors by different energy resources for scenario A and scenario B. So as we'd like to recall that scenario A is a high carbon tax scenario, and scenario B is carbon neutrality scenario, which is stricter than the scenario A in terms of carbon emission. As you can see from the figure, under both scenarios, the consumption of fossil energies such as coal and some oil-related products will be significantly reduced till 2050. However, in scenario A, the consumption of natural gas will remain very stable at around 350 terawatt per year, accounting for about 25% of final energy demand. And in scenario B, the market share of natural gas will gradually reduce from the year of 2040. And in 2050, it only speaks for 11% of final energy demand. Another finding is that in scenario B, the final energy demand for fossil energies will be replaced by electricity and renewable heat. So by 2050, electricity will speak for around 50% of national energy demand. So next is if we focus on the residential sector, scenario A and scenario B present very difficult, very different technological pathway. So due to time limits, I will just present to you what will happen for the scenario B. So for this scenario, the usage of renewable heat for heating pumps will rapidly increase from the year of 2040. And in 2050, it accounts for around 30% of energy demand. And from the year of 2035, the consumption of biomass will be gradually replaced by electrification and building insulation. So the next result that I would like to present to you is a comparison between scenario D and scenario B. So in scenario D, we suppose that the household in group 1 have more difficulties to access to capital, while in scenario B, no difference between two household groups. So as you can see, if households have less access to capital, so instead of doing insulation, which is quite heavy investment for the residential sector, this sector will use more electricity and district heat. So another type of result that the model can show us is the evolution of the total annual investment cost of French energy system. So the scenario D presents the highest investment cost among all scenarios, which means that the stricter carbon emission constraints and budget constraints will lead to a higher investment cost for the energy system. So next, I will present you our main conclusions from this preliminary result, modeling results, and the perspectives on the future work. So we have four main conclusions. Firstly, we find out that a stricter environmental constraint will lead to a deeper decarbonization of French energy system. For example, there will be a sharp reduce of natural gas usages from 25% in 2020 to 11% in 2050. And another phenomenon or another result will illustrate the massive electrification of 50% in 2050. And secondly, or more specifically for the residential sector, the usage of biomass will reach to about 50% under a high CO2 tax scenario, while under a more ambitious carbon reduction objective, and there will be more usages of renewable heat and building insulation. And thirdly, if households have more difficulties to access the capital, they will, or for the energy saving investments, they will more rely on heating pumps other than building insulation. And the last conclusion shows that our preliminary results support the idea of accounting for residential, social, technological interaction in times model. And for our future work, we will try to work on a more detailed representation of French housing stock from socio-economic perspective. And another axis will be, we'll try to carry on some further studies on technological potentials of certain new heating energies, such as gas heating pumps, heat storage, and biomass, etc. So thank you for the listening. I'm looking forward to the discussion.
Thank you very much. Do you have any questions in chat or microphone? No remarks? Question in the chat?
Yep.
Zixuan?
Yep. I just cannot find the
yes.
Maybe I stop sharing my screen so that I can see the question.
Actually, I can also just ask the question if that's easier for you, because thank you very much. Thank you very much for your presentation. At first, I was just wondering about the results. I think it was the second slides of the results which you presented, where from 2040 onwards, you suddenly had this increase in renewable heat. No, I think one further. Yes, this one, where this one or the one afterwards, basically in 2040 you suddenly have this like increase of renewable heat which you don't see before at all, and which you don't see in like other scenarios. And I was wondering, like, what is it that changes exactly at this cutoff date which makes renewable heat the most cost efficient solution for many households?
Yeah, exactly, because so the scenario A, so this is a result of two scenarios. Scenario A is a high carbon tax scenario, and scenario B is carbon neutrality scenario. So the main difference of the two scenarios lies on the level of the carbon constraints. So for the scenario B, there will be stricter carbon emission constraint. So given that the times model is so the optimization process of times model is based on the economical, environmental, and technical standards. And for the scenario B, in order to respect this strict carbon constraint, so there should be some more usage of clean energy in the energy system. Even though that the investment cost of the renewable heat for the heating pump is very much higher than the other usage of energy. So yeah, it's a cost problem. It's a cost question, and it's also an environmental constraint influential factor. I'm not
okay, thank you.
Have replied to your question.
Other questions?
Yeah.
No more? Okay. Oh, thank you very much for your presentation and discussion. And thank you all for your attention and presentation for this, this very interesting session. And see you soon for the next step of the conference. Bye, everybody. Thank you.
Thank you. And
Thanks for being the host. Thanks for the questions. Goodbye, everybody.
Yeah, thank you. Goodbye.
And just a quick reminder of uploading the slides, please, to the participants in the dashboard. Okay.
So can you say that again? The uploading them?
Yeah. If
the conference dashboard?
In the conference dashboard, if you could please upload the slides from today's presentation. Please.
Okay. Okay.
Great. Thank you very much, everybody.
Thank you. Bye.
Bye.
Thank you.
Bye.